Coaxial cable, or coax pronounced, is a type of electrical cable that has an inner conductor surrounded by a tubular insulating layer, surrounded by a tubular conducting shield. Many coaxial cables also have an insulating outer sheath or jacket. The term coaxial comes from the inner conductor and the outer shield sharing a geometric axis. Coaxial cable was invented by English engineer and mathematician Oliver Heaviside, who patented the design in 1880. Coaxial cable is a type of transmission line, used to carry high-frequency electrical signals with low losses. It is used in such applications as telephone trunklines, broadband Internet networking cables, high-speed computer data buses, carrying cable television signals, and connecting radio transmitters and receivers to their antennas. It differs from other shielded cables because the dimensions of the cable and connectors are controlled to give a precise, constant conductor spacing, which is needed for it to function efficiently as a transmission line. Applications. Coaxial cable is used as a transmission line for radio frequency signals. Its applications include feedlines connecting radio transmitters and receivers to their antennas, computer network Internet connections, digital audio (SPDIF), and distributing cable television signals. One advantage of coaxial over other types of radio transmission line is that in an ideal coaxial cable the electromagnetic field carrying the signal exists only in the space between the inner and outer conductors. This allows coaxial cable runs to be installed next to metal objects such as gutters without the power losses that occur in other types of transmission lines. Coaxial cable also provides protection of the signal from external electromagnetic interference. Topic: Description. Coaxial cable conducts electrical signal using an inner conductor, usually a solid copper, stranded copper or copper-plated steel wire, surrounded by an insulating layer and all enclosed by a shield, typically 1 to 4 layers of woven metallic braid and metallic tape. The cable is protected by an outer insulating jacket. Normally, the shield is kept at ground potential and a signal-carrying voltage is applied to the center conductor. The advantage of coaxial design is that electric and magnetic fields are restricted to the dielectric with little leakage outside the shield. Conversely, electric and magnetic fields outside the cable are largely kept from interfering with signals inside the cable. Larger diameter cables and cables with multiple shields have less leakage. This property makes coaxial cable a good choice for carrying weak signals that cannot tolerate interference from the environment or for stronger electrical signals that must not be allowed to radiate or couple into adjacent structures or circuits. Common applications of coaxial cable include video and CATV distribution, RF and microwave transmission, and computer and instrumentation data connections. The characteristic impedance of the cable Z 0 (Z_0) is determined by the dielectric constant of the inner insulator and the radii of the inner and outer conductors. A controlled cable characteristic impedance is important because the source and load impedance should be matched to ensure maximum power transfer and minimum standing wave ratio. Other important properties of coaxial cable include attenuation as a function of frequency, voltage handling capability, and shield quality. Construction. Coaxial cable design choices affect physical size, frequency performance, attenuation, power handling capabilities, flexibility, strength, and cost. The inner conductor might be solid or stranded. Stranded is more flexible. To get better high-frequency performance, the inner conductor may be silver-plated. Copper-plated steel wire is often used as an inner conductor for cable used in the cable TV industry. The insulator surrounding the inner conductor may be solid plastic, a foam plastic, or air with spaces supporting the inner wire. The properties of the dielectric insulator determine some of the electrical properties of the cable. A common choice is a solid polyethylene (P) insulator, used in lower loss cables. Solid Teflon (PTFE) is also used as an insulator. Some coaxial lines use air or some other gas and have spaces to keep the inner conductor from touching the shield. Many conventional coaxial cables use braided copper wire forming the shield. This allows the cable to be flexible, but it also means there are gaps in the shield layer, and the inner dimension of the shield varies slightly because the braid cannot be flat. Sometimes the braid is silver-plated. For better shield performance, some cables have a double-layer shield. The shield might be just 2 braids, but it is more common now to have a thin foil shield covered by a wire braid. Some cables may invest in more than 2 shield layers, such as quad shield, which uses 4 alternating layers of foil and braid. Other shield designs sacrifice flexibility for better performance. Some shields are a solid metal tube. Those cables cannot be bent sharply, as the shield will kink, causing losses in the cable. When a foil shield is used, a small wire conductor incorporated into the foil makes soldering the shield termination easier. For high-power radio frequency transmission up to about 1 GHz, coaxial cable with a solid copper outer conductor is available in sizes of 0.25 inch upward. The outer conductor is corrugated like a bellows to permit flexibility, and the inner conductor is held in position by a plastic spiral to approximate an air dielectric. One brand name for such cable is Heliax. Coaxial cables require an internal structure of an insulating dielectric material to maintain the spacing between the center conductor and shield. The dielectric losses increase in this order: ideal dielectric, no loss, vacuum, air, polytetrafluoroethylene (PTFE), polyethylene foam, and solid polyethylene. A low relative permittivity allows for higher frequency usage. An inhomogeneous dielectric needs to be compensated by a non-circular conductor to avoid current hot spots. While many cables have a solid dielectric, many others have a foam dielectric that contains as much air or other gas as possible to reduce the losses by allowing the use of a larger diameter center conductor. Foam coax will have about 15% less attenuation, but some types of foam dielectric can absorb moisture, especially at its many surfaces, in humid environments, significantly increasing the loss. Supports shaped like stars or spokes are even better but more expensive and very susceptible to moisture infiltration. Still more expensive were the air-spaced coaxials used for some intercity communications in the mid-20th century. The center conductor was suspended by polyethylene discs every few centimeters. In some low-loss coaxial cables such as the RG62 type, the inner conductor is supported by a spiral strand of polyethylene, so that an air space exists between most of the conductor and the inside of the jacket. The lower dielectric constant of air allows for a greater inner diameter at the same impedance and a greater outer diameter at the same cutoff frequency, lowering ohmic losses. Inner conductors are sometimes silver-plated to smooth the surface and reduce losses due to skin effect. A rough surface extends the current path and concentrates the current at peaks, thus increasing ohmic loss. The insulating jacket can be made from many materials. A common choice is PVC, but some applications may require fire-resistant materials. Outdoor applications may require the jacket to resist ultraviolet light, oxidation, rodent damage, or direct burial. Flooded coaxial cables use a water-blocking gel to protect the cable from water infiltration through minor cuts in the jacket. For internal chassis connections, the insulating jacket may be omitted. Signal propagation. Twin lead transmission lines have the property that the electromagnetic wave propagating down the line extends into the space surrounding the parallel wires. These lines have low loss, but also have undesirable characteristics. They cannot be bent, tightly twisted, or otherwise shaped without changing their characteristic impedance, causing reflection of the signal back toward the source. They also cannot be buried or run along or attached to anything conductive, as the extended fields will induce currents in the nearby conductors, causing unwanted radiation and detuning of the line. Coaxial lines largely solve this problem by confining virtually all of the electromagnetic wave to the area inside the cable. Coaxial lines can therefore be bent and moderately twisted without negative effects, and they can be strapped to conductive supports without inducing unwanted currents in them. In radio frequency applications up to a few gigahertz, the wave propagates primarily in the transverse electric magnetic mode, which means that the electric and magnetic fields are both perpendicular to the direction of propagation. However, above a certain cutoff frequency, transverse electric or transverse magnetic trademark modes can also propagate, as they do in a waveguide. It is usually undesirable to transmit signals above the cutoff frequency, since it may cause multiple modes with different phase velocities to propagate, interfering with each other. The outer diameter is roughly inversely proportional to the cutoff frequency. A propagating surface wave mode that does not involve or require the outer shield but only a single central conductor also exists in coax, but this mode is effectively suppressed in coax of conventional geometry and common impedance. Electric field lines for this trademark mode have a longitudinal component and require line lengths of a half wavelength or longer. Coaxial cable may be viewed as a type of waveguide. Power is transmitted through the radial electric field and the circumferential magnetic field in the TEMOO transverse mode. This is the dominant mode from zero frequency DC to an upper limit determined by the electrical dimensions of the cable. Topic: Connectors. The ends of coaxial cables usually terminate with connectors. Coaxial connectors are designed to maintain a coaxial form across the connection and have the same impedance as the attached cable. Connectors are usually plated with high conductivity metals such as silver or tarnish-resistant gold. Due to the skin effect, the RF signal is only carried by the plating at higher frequencies and does not penetrate to the connector body. Silver, however, tarnishes quickly and the silver sulfide that is produced is poorly conductive, degrading connector performance, making silver a poor choice for this application. Important parameters. Coaxial cable is a particular kind of transmission line, so the circuit models developed for general transmission lines are appropriate. See telegrapher's equation. Topic: Physical parameters. In the following section, these symbols are used. Length of the cable h displaystyle h. Outside diameter of inner conductor d displaystyle d. Inside diameter of the shield d displaystyle d. Dielectric constant of the insulator E displaystyle epsilon. The dielectric constant is often quoted as the relative dielectric constant ER displaystyle epsilon underscore r, referred to the dielectric constant of free space E0 displaystyle epsilon underscore 0. E equals ER E0 displaystyle epsilon equals epsilon underscore r epsilon underscore 0. When the insulator is a mixture of different dielectric materials, e.g., polyethylene foam is a mixture of polyethylene and air, then the term effective dielectric constant E F F displaystyle epsilon underscore F is often used. Magnetic permeability of the insulator mu displaystyle mu. Permeability is often quoted as the relative permeability mu r displaystyle mu underscore r, referred to the permeability of free space mu 0 displaystyle mu underscore 0. Mu equals mu r mu 0 displaystyle mu equals mu underscore r mu underscore 0. The relative permeability will almost always be 1. Topic: Fundamental electrical parameters. Shunt capacitance per unit length in farads per meter. C H equals 2 pi E lane D D equals 2 pi E0 ER lane D D. Display style left frac c h right equals 2 pi epsilon over lane d d equals 2 pi epsilon underscore 0 epsilon underscore r over lane d d. Series inductance per unit length in henries per meter. L H equals mu 2 pi lane d d equals mu 0 mu r 2 pi lane d d. Display style left frac L H right equals mu over 2 pi lane d d equals mu underscore 0 mu underscore r over 2 pi lane d d. Series resistance per unit length in ohms per meter. The resistance per unit length is just the resistance of inner conductor and the shield at low frequencies. At higher frequencies, skin effect increases the effective resistance by confining the conduction to a thin layer of each conductor. Shunt conductance per unit length, in Siemens per meter. The shunt conductance is usually very small because insulators with good dielectric properties are used, a very low loss tangent. At high frequencies, a dielectric can have a significant resistive loss. Derived electrical parameters. Characteristic impedance in ohms omega. The complex impedance Z of an infinite length of transmission line is Z equals R plus S L G plus S C. Display style Z equals sqrt frac R plus SL G plus SC, where R is the resistance per unit length, L is the inductance per unit length, G is the conductance per unit length of the dielectric, C is the capacitance per unit length, and S. Topic J omega. J2 pi f is the frequency. The per unit length dimensions cancel out in the impedance formula. At very low frequencies S approximately equals 0, the two reactive terms are negligible, so the impedance is real valued and looks like Z D C equals R G. Display style Z underscore mathrm DC equals sqrt frac R G. With increasing frequency, the reactive components take effect and the impedance of the line is complex valued. At higher frequencies, the reactive terms usually dominate R and G, and the cable impedance again becomes real valued. That value is Z0, the characteristic impedance of the cable. Z0 equals S L S C equals L C. Display style Z underscore 0 equals sqrt frac SL SC equals sqrt frac L C. Assuming the dielectric properties of the material inside the cable do not vary appreciably over the operating range of the cable, the characteristic impedance is frequency independent above about 5 times the shield cutoff frequency. For typical coaxial cables, the shield cutoff frequency is 600 Rg6A to 2000 Hz Rg58C. The parameters L and C are determined from the ratio of the inner D and outer D diameters and the dielectric constant epsilon. The characteristic impedance is given by Z 0 equals 1 2 pi mu lane D D approximately equals 60 omega ER lane D D approximately equals 138 omega ER log 10 D D display style z underscore 0 equals frac 1 2 pi sqrt frac mu epsilon lane frac d approximately frac 60 omega sqrt epsilon underscore r lane frac d approximately frac 138 omega sqrt epsilon underscore r log underscore 10 frac d attenuation loss per unit length, in decibels per meter. This is dependent on the loss in the dielectric material filling the cable, and resistive losses in the center conductor and outer shield. These losses are frequency dependent, the losses becoming higher as the frequency increases. Skin effect losses in the conductors can be reduced by increasing the diameter of the cable. A cable with twice the diameter will have half the skin effect resistance. Ignoring dielectric and other losses, the larger cable would halve the decibel per meter loss. In designing a system, engineers consider not only the loss in the cable but also the loss in the connectors. Velocity of propagation, in meters per second. The velocity of propagation depends on the dielectric constant and permeability, which is usually 1 v equals 1 e mu equals c er mu r. Display style v equals 1 over sqrt epsilon mu equals c over sqrt epsilon underscore r mu underscore r. Single mode band. In coaxial cable, the dominant mode, the mode with the lowest cutoff frequency, is the TEM mode, which has a cutoff frequency of 0. It propagates all the way down to d.c. The mode with the next lowest cutoff is the TE11 mode. This mode has one wave, two reversals of polarity in going around the circumference of the cable. To a good approximation, the condition for the TE11 mode to propagate is that the wavelength in the dielectric is no longer than the average circumference of the insulator, that is that the frequency is at least f c approximately equals 1 pi d plus d 2 mu e equals c pi d plus d 2 mu r er. Display style f underscore c approximately 1 over pi d plus d over 2 sqrt mu epsilon equals c over pi d plus d over 2 sqrt mu underscore r epsilon underscore r. Hence, the cable is single mode from to d.c. up to this frequency, and might in practice be used up to 90% of this frequency, peak voltage. The peak voltage is set by the breakdown voltage of the insulator. One website gives V P equals 1150 S mils d in log 10 d display style v underscore p equals 1150 s underscore text mils d underscore text in log underscore 10 left frac d right, where Smiles is the insulator's breakdown voltage in volts per mil. Din is the inner diameter in inches. The 1150 factor converts inches diameter to mils radius and log 10 to lane. The above expression may be rewritten as V P equals 0.5 S D lane D D display style V underscore P equals 0.5 S D lane left frac D D right, where S is the insulator's breakdown voltage in volts per meter, D is the inner diameter in meters. The calculated peak voltage is often reduced by a safety factor. Topic: Choice of impedance. The best coaxial cable impedances in high power, high voltage, and low attenuation applications were experimentally determined at Bell Laboratories in 1929 to be 30, 60, and 77 ohms, respectively. For a coaxial cable with air dielectric and a shield of a given inner diameter, the attenuation is minimized by choosing the diameter of the inner conductor to give a characteristic impedance of 76.7 ohms. When more common dielectrics are considered, the best loss impedance drops down to a value between 52 to 64 ohms. Maximum power handling is achieved at 30 ohms. The approximate impedance required to match a center-fed dipole antenna in free space, i.e., a dipole without ground reflections, is 73 ohms, so 75 ohms coax was commonly used for connecting shortwave antennas to receivers. These typically involve such low levels of RF power that power handling and high voltage breakdown characteristics are unimportant when compared to attenuation. Likewise with CATV, although many broadcast TV installations and CATV headends use 300 ohms folded dipole antennas to receive off-the-air signals, 75 ohms coax makes a convenient 4-to-1 balloon transformer for these as well as possessing low attenuation. The arithmetic mean between 30 ohms and 77 ohms is 53.5 ohms, the geometric mean is 48 ohms. The selection of 50 ohms as a compromise between power handling capability and attenuation is in general cited as the reason for the number. 50 ohms also works out tolerably well because it corresponds approximately to the drive impedance, ideally 36 ohms, of a quarter-wave monopole, mounted on a less than optimum ground plane such as a vehicle roof. The match is better at low frequencies, such as for CB radio around 27 MHz, where the roof dimensions are much less than a quarter wavelength, and relatively poor at higher frequencies, VHF and UHF, where the roof dimensions may be several wavelengths. The match is at best poor, because the antenna drive impedance, due to the imperfect ground plane, is reactive rather than purely resistive, and so a 36-ohm coaxial cable would not match properly either. Installations which need exact matching will use some kind of matching circuit at the base of the antenna, or elsewhere, in conjunction with a carefully chosen in terms of wavelength length of coaxial, such that a proper match is achieved, which will be only over a fairly narrow frequency range. RG62 is a 93 ohms coaxial cable originally used in mainframe computer networks in the 1970s and early 1980s. It was the cable used to connect IBM 3270 terminals to IBM 3274 3174 terminal cluster controllers. Later, some manufacturers of LAN equipment, such as Datapoint for ARC-NET, adopted RG62 as their coaxial cable standard. The cable has the lowest capacitance per unit length when compared to other coaxial cables of similar size. All of the components of a coaxial system should have the same impedance to avoid internal reflections at connections between components. Such reflections may cause signal attenuation and ghosting TV picture display. Multiple reflections may cause the original signal to be followed by more than one echo. In analog video or TV systems, this causes ghosting in the image. Reflections also introduce standing waves, which cause increased losses and can even result in cable dielectric breakdown with high power transmission. See impedance matching. Briefly, if a coaxial cable is open, the termination has nearly infinite resistance. This causes reflections. If the coaxial cable is short-circuited, the termination resistance is nearly zero. There will be reflections with the opposite polarity. Reflection will be nearly eliminated if the coaxial cable is terminated in a pure resistance equal to its impedance. Coaxial characteristic impedance derivation. Taking the characteristic impedance at high frequencies Z 0 equals L C display style Z underscore 0 equals sqrt frac L C. One should also know the inductance and capacitance of the two concentric cylindrical conductors, which is the coaxial cable. By definition, C equals Q V display style C equals Q V, and getting the electric field by the formula of electric field of an infinite line E equals Q 2 pi EO R caret R display style VEC equals frac Q 2 pi epsilon underscore O frac hat R, where Q display style Q is charge, EO display style epsilon underscore O is the permittivity of free space, R display style R is the radial distance, and R caret display style hat R is the unit vector in the direction away from the axis. Voltage is then V equals E D equals minus D Q 2 pi EO R D R equals Q 2 pi EO L N D display style V equals ed equals int underscore D caret D frac Q 2 pi epsilon underscore O R doctor equals frac Q 2 pi epsilon underscore O lane frac D where D display style D is the diameter of the bigger conductor and D display style D is the diameter of the smaller conductor. The capacitance can then be solved by substitution. C equals Q V equals 2 pi EO L N D display style C equals frac Q V equals frac 2 pi epsilon underscore O lane frac D D, and the inductance is taken from Ampere's law for two concentric conductors coaxial wire, and with the definition of inductance B equals mu O I 2 pi R, display style B equals frac mu underscore O I 2 pi R, and L equals phi I equals B I D S, display style L equals frac phi I equals int frac B I ds, where B display style B is magnetic induction, mu O display style mu underscore O is the permeability of free space, phi display style phi is the magnetic flux, and d s display style ds is the differential surface. Taking the inductance per meter L equals d d mu O 2 pi R D R equals mu O 2 pi L N D D, display style L equals int limits underscore D caret D frac mu underscore O 2 pi R doctor equals frac mu underscore O 2 pi lane frac D D. Substituting the derived capacitance and inductance Z 0 equals L C equals 1 2 pi mu E lane D D, display style Z underscore 0 equals sqrt frac L C equals frac 1 2 pi sqrt frac mu epsilon lane frac D D. Topic: Issues. Topic: Signal leakage. Signal leakage is the passage of electromagnetic fields through the shield of a cable and occurs in both directions. Ingress is the passage of an outside signal into the cable and can result in noise and disruption of the desired signal. Egress is the passage of signal intended to remain within the cable into the outside world and can result in a weaker signal at the end of the cable and radio frequency interference to nearby devices. Severe leakage usually results from improperly installed connectors or faults in the cable shield. For example, in the United States, signal leakage from cable television systems is regulated by the FCC, since cable signals use the same frequencies as aeronautical and radio navigation bands. CATV operators may also choose to monitor their networks for leakage to prevent ingress. Outside signals entering the cable can cause unwanted noise and picture ghosting. Excessive noise can overwhelm the signal, making it useless. An ideal shield would be a perfect conductor with no holes, gaps, or bumps connected to a perfect ground. However, a smooth solid highly conductive shield would be heavy, inflexible, and expensive. Such coax is used for straight-line feeds to commercial radio broadcast towers. More economical cables must make compromises between shield efficacy, flexibility, and cost, such as the corrugated surface of flexible hardline, flexible braid, or foil shields. Since shields cannot be perfect conductors, current flowing on the inside of the shield produces an electromagnetic field on the outer surface of the shield. Consider the skin effect. The magnitude of an alternating current in a conductor decays exponentially with distance beneath the surface, with the depth of penetration being proportional to the square root of the resistivity. This means that, in a shield of finite thickness, some small amount of current will still be flowing on the opposite surface of the conductor. With a perfect conductor, i.e., zero resistivity, all of the current would flow at the surface, with no penetration into and through the conductor. Real cables have a shield made of an imperfect, although usually very good, conductor, so there must always be some leakage. The gaps or holes allow some of the electromagnetic field to penetrate to the other side. For example, braided shields have many small gaps. The gaps are smaller when using a foil solid metal shield, but there is still a seam running the length of the cable. Foil becomes increasingly rigid with increasing thickness, so a thin foil layer is often surrounded by a layer of braided metal, which offers greater flexibility for a given cross-section. Signal leakage can be severe if there is poor contact at the interface to connectors at either end of the cable or if there is a break in the shield. To greatly reduce signal leakage into or out of the cable, by a factor of 1,000, or even 10,000, superscreened cables are often used in critical applications, such as for neutron flux counters in nuclear reactors. Superscreened cables for nuclear use are defined in IEC 1 April 1990. However, as there have been long gaps in the construction of nuclear power stations in Europe, many existing installations are using superscreened cables to the UK standard AESS TRG 71181, which is referenced in IEC 61917. Ground loops. A continuous current, even if small, along the imperfect shield of a coaxial cable can cause visible or audible interference. In CATV systems distributing analog signals, the potential difference between the coaxial network and the electrical grounding system of a house can cause a visible hum bar in the picture. This appears as a wide horizontal distortion bar in the picture that scrolls slowly upward. Such differences in potential can be reduced by proper bonding to a common ground at the house. See ground loop. Noise. External fields create a voltage across the inductance of the outside of the outer conductor between sender and receiver. The effect is less when there are several parallel cables, as this reduces the inductance and, therefore, the voltage. Because the outer conductor carries the reference potential for the signal on the inner conductor, the receiving circuit measures the wrong voltage. Transformer effect. The transformer effect is sometimes used to mitigate the effect of currents induced in the shield. The inner and outer conductors form the primary and secondary winding of the transformer, and the effect is enhanced in some high-quality cables that have an outer layer of mu metal. Because of this one-to-one transformer, the aforementioned voltage across the outer conductor is transformed onto the inner conductor so that the two voltages can be cancelled by the receiver. Many sender and receivers have means to reduce the leakage even further. They increase the transformer effect by passing the whole cable through a ferrite core one or more times. Common mode current and radiation. Common mode current occurs when stray currents in the shield flow in the same direction as the current in the center conductor, causing the coax to radiate. Most of the shield effect in coax results from opposing currents in the center conductor and shield creating opposite magnetic fields that cancel, and thus do not radiate. The same effect helps ladder line. However, ladder line is extremely sensitive to surrounding metal objects, which can enter the fields before they completely cancel. Coax does not have this problem, since the field is enclosed in the shield. However, it is still possible for a field to form between the shield and other connected objects, such as the antenna the coax feeds. The current formed by the field between the antenna and the coax shield would flow in the same direction as the current in the center conductor, and thus not be cancelled. Energy would radiate from the coax itself, affecting the radiation pattern of the antenna. With sufficient power, this could be a hazard to people near the cable. A properly placed and properly sized balloon can prevent common mode radiation in coax. An isolating transformer or blocking capacitor can be used to couple a coaxial cable to equipment, where it is desirable to pass radio frequency signals but to block direct current or low-frequency power. Standards. Most coaxial cables have a characteristic impedance of either 50, 52, 75, or 93 ohms. The RF industry uses standard type names for coaxial cables. Thanks to television, RG6 is the most commonly used coaxial cable for home use, and the majority of connections outside Europe are by F connectors. A series of standard types of coaxial cable were specified for military uses, in the form RG# or RG#U. They date from World War II and were listed in MIL HDBK 216 published in 1962. These designations are now obsolete. The RG designation stands for radio guide, the U designation stands for universal. The current military standard is mil-spec mil-C17. Mil-C17 numbers, such as M17, 75RG214, are given for military cables and manufacturers' catalog numbers for civilian applications. However, the RG series designations were so common for generations that they are still used, although critical users should be aware that since the handbook is withdrawn there is no standard to guarantee the electrical and physical characteristics of a cable described as RG# type. The RG designators are mostly used to identify compatible connectors that fit the inner conductor, dielectric, and jacket dimensions of the old RG series cables. Dielectric material codes. FPE is foamed polyethylene. P is solid polyethylene. PF is polyethylene foam. PTFE is polytetrafluoroethylene. ASP is airspace polyethylene. VF is the velocity factor. It is determined by the effective ER display style epsilon underscore r and mu r display style mu underscore r. Vf for solid P is about 0.66. Vf for foam P is about 0.78 to 0.88. Vf for air is about 1.00. Vf for solid PTFE is about 0.70. Vf for foam PTFE is about 0.84. There are also other designation schemes for coaxial cables such as the URM, CT, BT, Ra, PSF and WF series. Topic: Uses. Short coaxial cables are commonly used to connect home video equipment, in ham radio setups, and in measurement electronics. While formerly common for implementing computer networks, in particular Ethernet, thick 10BASE5 and thin 10BASE2, twisted pair cables have replaced them in most applications except in the growing consumer cable modem market for broadband Internet access. Long-distance coaxial cable was used in the 20th century to connect radio networks, television networks, and long-distance telephone networks, though this has largely been superseded by later methods: fiber optics, T1, E1, satellite. Shorter coaxials still carry cable television signals to the majority of television receivers, and this purpose consumes the majority of coaxial cable production. In 1980s and early 1990s, coaxial cable was also used in computer networking, most prominently in Ethernet networks, where it was later in late 1990s to early 2000s replaced by UTP cables in North America and STP cables in Western Europe, both with 8P8C modular connectors. Microcoaxial cables are used in a range of consumer devices, military equipment, and also in ultrasound scanning equipment. The most common impedances that are widely used are 50 or 52 ohms, and 75 ohms, although other impedances are available for specific applications. The 50-50 ohm cables are widely used for industrial and commercial two-way radio frequency applications including radio, and telecommunications, although 75 ohms is commonly used for broadcast television and radio. Coax cable is often used to carry data, signals from an antenna to a receiver, from a satellite dish to a satellite receiver, from a television antenna to a television receiver, from a radio mast to a radio receiver, etc. In many cases, the same single coax cable carries power in the opposite direction, to the antenna, to power the low-noise amplifier. In some cases a single coax cable carries unidirectional power and bidirectional data, signals, as in DIS-EQC. Types. Hard line. Hard line is used in broadcasting as well as many other forms of radio communication. It is a coaxial cable constructed using round copper, silver or gold tubing or a combination of such metals as a shield. Some lower quality hardline may use aluminum shielding. Aluminum, however, is easily oxidized, and unlike silver oxide, aluminum oxide drastically loses effective conductivity. Therefore, all connections must be air and water tight. The center conductor may consist of solid copper, or copper-plated aluminum. Since skin effect is an issue with RF, copper plating provides sufficient surface for an effective conductor. Most varieties of hardline used for external chassis or when exposed to the elements have a PVC jacket, however, some internal applications may omit the insulation jacket. Hardline can be very thick, typically at least a ½ inch or 13 mm and up to several times that, and has low loss even at high power. These large-scale hard lines are almost always used in the connection between a transmitter on the ground and the antenna or aerial on a tower. Hard line may also be known by trademarked names such as Heliax (CommScope) or Cablewave (RFS, Cablewave). Larger varieties of hard line may have a center conductor that is constructed from either rigid or corrugated copper tubing. The dielectric in hard line may consist of polyethylene foam, air, or a pressurized gas such as nitrogen or desiccated air, dried air. In gas-charged lines, hard plastics such as nylon are used as spacers to separate the inner and outer conductors. The addition of these gases into the dielectric space reduces moisture contamination, provides a stable dielectric constant, and provides a reduced risk of internal arcing. Gas-filled hardlines are usually used on high-power RF transmitters such as television or radio broadcasting, military transmitters, and high-power amateur radio applications, but may also be used on some critical lower-power applications such as those in the microwave bands. However, in the microwave region, waveguide is more often used than hard line for transmitter to antenna, or antenna to receiver applications. The various shields used in hard line also differ, some forms use rigid tubing, or pipe, while others may use a corrugated tubing, which makes bending easier, as well as reduces kinking when the cable is bent to conform. Smaller varieties of hard line may be used internally in some high-frequency applications, in particular in equipment within the microwave range, to reduce interference between stages of the device. Radiating. Radiating or leaky cable is another form of coaxial cable which is constructed in a similar fashion to hard line, however it is constructed with tuned slots cut into the shield. These slots are tuned to the specific RF wavelength of operation or tuned to a specific radio frequency band. This type of cable is to provide a tuned bidirectional, desired leakage effect between transmitter and receiver. It is often used in elevator shafts, U.S. Navy ships, underground transportation tunnels and in other areas where an antenna is not feasible. One example of this type of cable is Radiax CommScope. RG6. RG6 is available in 4 different types designed for various applications. In addition, the core may be copper-clad steel (CCS) or bare solid copper (BC), plain, or house. RG6 is designed for indoor or external house wiring. Flooded cable is infused with water-blocking gel for use in underground conduit or direct burial. Messenger may contain some waterproofing but is distinguished by the addition of a steel messenger wire along its length to carry the tension involved in an aerial drop from a utility pole. Plenum cabling is expensive and comes with a special Teflon-based outer jacket designed for use in ventilation ducts to meet fire codes. It was developed since the plastics used as the outer jacket and inner insulation in many plain or house cabling gives off poison gas when burned. Triaxial cable. Triaxial cable or triax is coaxial cable with a third layer of shielding, insulation and sheathing. The outer shield, which is earthed-grounded, protects the inner shield from electromagnetic interference from outside sources. Twin axial cable. Twin axial cable or twinax is a balanced, twisted pair within a cylindrical shield. It allows a nearly perfect differential signal which is both shielded and balanced to pass through. Multi-conductor coaxial cable is also sometimes used. Semi-rigid. Semi-rigid cable is a coaxial form using a solid copper outer sheath. This type of coax offers superior screening compared to cables with a braided outer conductor, especially at higher frequencies. The major disadvantage is that the cable, as its name implies, is not very flexible, and is not intended to be flexed after initial forming. See hard line. Conformable cable is a flexible reformable alternative to semi-rigid coaxial cable used where flexibility is required. Conformable cable can be stripped and formed by hand without the need for specialized tools, similar to standard coaxial cable. Rigid line. Rigid line is a coaxial line formed by two copper tubes maintained concentric every other meter using PTFE supports. Rigid lines cannot be bent, so they often need elbows. Interconnection with rigid line is done with an inner bullet, inner support and a flange or connection kit. Typically, rigid lines are connected using standardized ARRF connectors whose bullet and flange sizes match the standard line diameters. For each outer diameter, either 75 or 50 ohm inner tubes can be obtained. Rigid line is commonly used indoors for interconnection between high-power transmitters and other RF components, but more rugged rigid line with weatherproof flanges is used outdoors on antenna masts, etc. In the interests of saving weight and costs, on masts and similar structures the outer line is often aluminium, and special care must be taken to prevent corrosion. With a flange connector, it is also possible to go from rigid line to hard line. Many broadcasting antennas and antenna splitters use the flanged rigid line interface even when connecting to flexible coaxial cables and hard line. Rigid line is produced in a number of different sizes. Cables used in the UK. At the start of analog satellite TV broadcasts in the UK by B-Sky-B, a 75 ohm cable referred to as RG6 was used. This cable had a 1 mm copper core, air-spaced polyethylene dielectric and copper braid on an aluminium foil shield. When installed outdoors without protection, the cable was affected by UV radiation, which cracked the PVC outer sheath and allowed moisture ingress. The combination of copper, aluminium, moisture and air caused rapid corrosion, sometimes resulting in a snake swallowed an egg appearance. Consequently, despite the higher cost, the RG6 cable was dropped in favor of CT100 when B-Sky-B launched its digital broadcasts. From around 1999 to 2005, when CT100 manufacturer Radix went out of business, CT100 remained the 75 ohm cable of choice for satellite TV and especially B-Sky-B. It had an air-spaced polyethylene dielectric, a 1 mm solid copper core and copper braid on copper foil shield. CT63 was a thinner cable in shotgun style, meaning that it was two cables molded together and was used mainly by B-SkyB for the twin connection required by the Sky Plus satellite TV receiver, which incorporated a hard drive recording system and a second, independent tuner. In 2005, these cables were replaced by WF100 and WF65, respectively, manufactured by Webro and having a similar construction but a foam dielectric that provided the same electrical performance as air-spaced but was more robust and less likely to be crushed. At the same time, with the price of copper steadily rising, the original RG6 was dropped in favor of a construction that used a copper-clad steel core and aluminium braid on aluminium foil. Its lower price made it attractive to aerial installers looking for a replacement for the so-called low-loss cable traditionally used for UK terrestrial aerial installations. This cable had been manufactured with a decreasing number of strands of braid, as the price of copper increased, such that the shielding performance of cheaper brands had fallen to as low as 40%. With the advent of digital terrestrial transmissions in the UK, this low-loss cable was no longer suitable. The new RG6 still performed well at high frequencies because of the skin effect in the copper cladding. However, the aluminium shield had a high DC resistance and the steel core an even higher one. The result is that this type of cable could not reliably be used in satellite TV installations, where it was required to carry a significant amount of current, because the voltage drop affected the operation of the low-noise block-down converter on the dish. A problem with all the aforementioned cables, when passing current, is that electrolytic corrosion can occur in the connections unless moisture and air are excluded. Consequently, various solutions to exclude moisture have been proposed. The first was to seal the connection by wrapping it with self-amalgamating rubberized tape, which bonds to itself when activated by stretching. The second proposal, by the American Channel Master Company, now owned by Andrews Corp., at least as early as 1999, was to apply silicone grease to the wires making connection. The third proposal was to fit a self-sealing plug to the cable. All of these methods are reasonably successful if implemented correctly. Interference and troubleshooting. Coaxial cable insulation may degrade, requiring replacement of the cable, especially if it has been exposed to the elements on a continuous basis. The shield is normally grounded, and if even a single thread of the braid or filament of foil touches the center conductor, the signal will be shorted, causing significant or total signal loss. This most often occurs at improperly installed end connectors and splicers. Also, the connector or splice must be properly attached to the shield, as this provides the path to ground for the interfering signal. Despite being shielded, interference can occur on coaxial cable lines. Susceptibility to interference has little relationship to broad cable type designations, e.g. RG59, RG6, but is strongly related to the composition and configuration of the cable's shielding. For cable television, with frequencies extending well into the UHF range, a foil shield is normally provided, and will provide total coverage as well as high effectiveness against high-frequency interference. Foil shielding is ordinarily accompanied by a tinned copper or aluminum braid shield, with anywhere from 60 to 95% coverage. The braid is important to shield effectiveness because 1, it is more effective than foil at preventing low-frequency interference, 2, it provides higher conductivity to ground than foil, and 3, it makes attaching a connector easier and more reliable. Quad shield Cable, using two low-coverage aluminum braid shields and two layers of foil, is often used in situations involving troublesome interference, but is less effective than a single layer of foil and single high-coverage copper braid shield such as is found on broadcast-quality precision video cable. In the United States and some other countries, cable television distribution systems use extensive networks of outdoor coaxial cable, often with inline distribution amplifiers. Leakage of signals into and out of cable TV systems can cause interference to cable subscribers and to over-the-air radio services using the same frequencies as those of the cable system. History 1880 – Coaxial cable patented in England by Oliver Heaviside, patent number 1407, 1884, Siemens & Halske patent coaxial cable in Germany patent number 28978, 27 March 1884, 1894, Nikola Tesla US patent 514167, 1929, first modern coaxial cable patented by Lloyd Espenschied and Hermann Affel of AT&T's Bell Telephone Laboratories, 1936, first closed-circuit transmission of TV pictures on coaxial cable, from the 1936 Summer Olympics in Berlin to Leipzig. 1936 – World's first underwater coaxial cable installed between Apollo Bay, near Melbourne, Australia, and Stanley, Tasmania. The 300 km cable can carry one 8.5-kHz broadcast channel and 7 telephone channels. 1936 – AT&T installs experimental coaxial telephone and television cable between New York and Philadelphia, with automatic booster stations every 10 miles. Completed in December, it can transmit 240 telephone calls simultaneously. 1936 – Coaxial cable laid by the General Post Office, now BT, between London and Birmingham, providing 40 telephone channels. 1941 – First commercial use in USA by AT&T, between Minneapolis, Minnesota and Stevens Point, Wisconsin. L1 system with capacity of 1 TV channel or 480 telephone circuits. 1949 – On January 11, 8 stations on the U.S. East Coast and 7 Midwestern stations are linked via a long-distance coaxial cable. 1956 – First transatlantic coaxial cable laid, TAT-1. See also: Balanced line, radio frequency power transmission, BNC connector, LEMO connector.